Well, it's a pleasure to be here today with all of you. I wish we were all in person so we could be meeting in the hallway track, but I really appreciate what Dyndrite has done to get together after we've missed a lot of the industry events here. It's also really heartwarming to hear everything that colleagues and other companies have been doing during this time of crisis. It really makes me proud to be part of this industry. I've always enjoyed the people here, and I'm not surprised, but certainly heartened to see the efforts of everybody. I'm going to take a slightly different tack here and talk about other stuff. I think it's kind of nice every once in a while to forget about what's going on with all the horrible news and talk tech for a little bit here. So let's get going. Title of my talk is Let's Kill STL, and let's start printing directly from CAD. But let me start out and give you a little bit of an introduction about Impossible Objects and who we are, because some people might not know us here. So Impossible Objects is a machine manufacturer. We have a proprietary platform called CBAM, or Composite-based Additive Manufacturing. We make the printers and the consumables that go into them for making composite parts. Right now we have carbon fiber based and fiberglass based materials. These are long fiber content parts with a variety of thermoplastics that we can use with them. These include nylon 12 and PEEK, and with more to come. We've made some announcements about some elastomerics and some thermosets, PA6, some other things, so stay tuned. But the real takeaway here is we have fast print times with very strong light parts. This is a little bit of an eye chart, I apologize, but this is a little bit about some of the material offerings we have: carbon fiber and PEEK, or nylon 12, fiberglass with PEEK. And what we end up with is high strength properties. It's very common for us to get 130 to 200 megapascals on the parts with chemical resistance and high heat tolerances. We also have a number of materials that are qualified for aerospace and medical. Switch gear. Let me show a quick video here of how our process works, and I'll talk through this with it on mute. This is a picture of our CBAM 2 machine here. We start with sheets of fabric. This is a non-woven carbon fiber material here. That's ½ inch long to inch long fibers in it. We then inkjet print a fluid onto it in the shape of your slice. This is actually not a glue or a binder. It's to help activate surface energies. We dust it with thermoplastic powder, and then we vacuum off the thermoplastic powder. It ends up sticking where we print it. So you end up with a sheet of carbon fiber with your thermoplastic selectively deposited on in the shape of your slice. Here's showing just some of the particles of plastic, thermoplastic embedded in the matrix. And the last step of the printing process is to stack these up on registration pins so that the images are vertically aligned. We then stick it into a heated press, put it under pressure and heat. The thermoplastic melts, it flows between the layers, and you get a solidified carbon fiber thermoplastic matrix here. And then the last step, which we'll see here in a second, is we either chemically or mechanically blast away the untreated fibers and release the part there. So we'll pause it there and go back to our presentation. Okay. We released our latest offering, the CBAM 2 machine, in Q1 of 2020. It's shipping in small volume at this point, and it's got a number of dramatic improvements over the previous generation, including bulk ink, bulk powder, camera-based inspection, 12 by 12 pages, improved reliability, industrial design improvements, a whole lot of things. And some parts that we make here just to show. This is showing the types of geometric complexities we can get. It's true additive manufacturing, and this is again a strong light carbon fiber part here. Nuts and bolts with good threading here. We'll talk in a second about why this is a trick. This is an aerospace benchmark part that's meant to trip up additive manufacturing processes, and we're very proud of the results we get there with overhangs and angles and small features, and particularly these side cuts and side holes. This is a part that we just flew in the B-1 bomber with some of our partners at the United States Air Force in UAMI. Very proud that we had a successful flight there, and we're looking forward to many more parts in the future. And if we had had an AMUG this year, we would have shown you this beautiful drone that we'd printed CBAM, and I guess we'll all have to wait till social nearnessing is back and we could all be in person to see it. I'm going to shift gears a little bit and talk about STL files. And so a little bit of background. STL was created as a stereolithography file. That's what STL stands for, in 1987 by some consultants working for 3D Systems. It's a very simple file format. All it does is specify triangles and their normals. And it's unfortunately still widely used, even though we've got a lot of other formats, AMF, 3MF, PLY, etc. out there. To give you an idea what I mean by simple and just triangles, this is what an STL file looks like. It's got a single text line, a header. There's also a binary equivalent that maps this. And then a second line that says the number of triangles. Then for each triangle, it shows a normal vector and 3 vertices and an attribute byte of 16 bits, an unsigned integer. You can try to put some data in there to go with it, color or material or something like that, but that tends to vary by vendor and it's not very much space to put something in. You know, just to show how stupid this format is, if you have a triangular mesh and these vertices are shared between different triangles, there's no way to indicate that. In fact, you have to go back and try to suss that out with your software to try to even figure out how the connectivity goes between the triangles. As a result, we got a number of problems with STL. A lot of invalid files come out. You've got T-intersections and non-manifold surfaces and bad formatting. So you end up bringing them into software that has to repair them and do a lot of processing on them. It's very basic. It doesn't have any color information. It's a single material. In fact, it doesn't specify the material at all. There's no metadata with it. No GD&T. For folks who aren't familiar with GD&T, this would be the dimensioning and tolerancing information that you have on a standard technical drawing, which gives a lot of hints for where you need to be careful and what types of tolerances you need to hold. A lot of information that can be very important for running your process. And the world is not made of triangles. If you tessellate a nice curve down to triangles, you know, your sphere becomes a soccer ball. And finally, it's a really lousy user experience here. As an example of what I was talking about, the tessellation, let's say we had this threaded bolt and a threaded collar that goes with it, and I'll zoom in on it. You end up tessellating it like this. Well, this is not a good way to get a good fit or a smooth turn of that threading when you have these coarse tessellations on it. So making things into triangles instead of using the real parametric surfaces they're based on, you start with 2 hands tied behind your back. And when I talk about a lousy user experience, this is what the pipeline looks like of getting an STL file to your printer. You first have to export it from your CAD. You then have to import it into some software. A lot of people are using things like Magix and NetFab. This is to read in the STL, repair it, get the connectivity put up. And then you need to make your build volume, get the thing onto your build plate, pack parts and nest parts together. Finally, you need to generate the files needed to get onto your printer. This might involve slicing. This might involve other aspects of building the file, and then get it onto your printer. There's a lot of steps. A lot of information is lost. A lot of chances for human error. The numerical error compounds every time you import and export this. You're getting a little further away from the data that you'd signed in the CAD. And finally, it's not secure. You're putting things on flash drives and on file systems and having printers access it and software access it, and it's a real mess. So we can look at a new model for this. What if we start printing directly from CAD? In this model, we put a build server in the middle here. This can be a separate machine and process. It could be in the cloud, on premise. It could be even with your printer. And from this, we can take CAD data in directly and serve your build information, your slices directly to your printer. One step better, by the way, is to talk directly to your CAD system here in a CAD server. So the build server here can not have to even export the step file, but talk directly to your CAD. And a lot of the software out there for CAD has APIs or is even cloud-based to allow you to do that and have nice authenticated secure access to your server and roles to see what it can and can't access. From there, you can look at sending over HTTP protocols here, which has the nice advantage that you could set up a firewall for security. It'll only open up these ports for HTTP up, And now I'm bringing a printer in, I'm putting it on my network, but I can lock it off in secure ways from being able to get to all my valuable data within my four walls here. So that's some of the advantage of this. It's a lot less steps here. It's a lot less data getting passed around. It keeps the metadata. It keeps the full CAD data. You don't have to tessellate, or if you do have to tessellate, you just do it as a last step and don't chain that inaccuracy. And you've got a secure chain of custody. So we're doing this at Impossible Objects, and we invite the rest of the industry to do this as we move from prototyping to manufacturing. We'd certainly love to partner to folks who also want to standardize on this. And we're extending this to a lot of things besides just the printing. Job queuing and build preparation, as I talked about with slicing and packing, job and printer statuses and dashboards, traveler workflow as the job moves across the floor. Traceability is an important part as we move to manufacturing, being able to keep track of which machine and which technician and even which bag of powder or bag of ink and where that came from in case there are problems. We also, as I mentioned, have cameras inspecting on our machines now. And this allows us to actually save the camera scan data to go look at if you want to do QA and QC or look up later why a part may have failed or you had a problem. Big piece of it also is integrating with the customer's ERP or MES system. Our machines don't live in a vacuum. You want to be able to integrate to the systems that your customers have in place, and it becomes important to do that. Offering these sorts of industry standard connectivity with REST APIs gives a really nice way of integrating between that, so you can have your customers' systems talking to your printers and getting this valuable data back. And finally, as I mentioned several times, doing this in a secure manner. Now, one question is, why are we at the Dyndrite meeting here? So let's talk about that for a second. We've been working with Dyndrite on integrating their kernel into our build server here. That allows us to read directly from CAD data, do fast slicing and slice serving. This could be on the server or within the printer. It's nice, it runs on a GPU, which is very inexpensive, and it takes the CPU load off of the main processor, allowing us to put it on the printer if we want. And stay tuned for a lot more features. I talked about packing, the build volumes. There's a lot more optimization and a lot of interesting features to come. And to tease Herschel a little bit from his speech this morning, what if we put Dyndrite in the CAD server? We don't have to transfer all that data at all. We can just transfer slices and you don't have those petabytes to go over the wire. I'd like to thank folks on my team here at Impossible Objects, Drew Salzman and Jeff Salzman and Drew Marshner, who've done a lot of our slicing work, and also the folks at Dyndrite and Herschel in particular for helping us with that. And I'd like to open it up to questions if we still have a few minutes here.
All right. Thank you, Len. We've got one. So how will this new system being developed, oh, make sure to stop sharing your screen.
Yep, I will try to do that.
There we go. Okay. So how will this new system by Impossible Objects help to enable a digital manufacturing ecosystem?
Well, I think there are a number of ways to do that. First of all, we are trying to make real production-ready parts with real material properties at fast rates that can meet the volume and throughput required for manufacturing. So first of all is to actually have decent parts that we can make and make in enough volume. The second piece is by integrating into the systems that you have at the user, at the customer site, that allows them to put it into their manufacturing environment. And this is a request we have, particularly from some of the regulated industries who say, we don't want to put your machine on our network and expose this. How can we do this in a secure way? So this allows us to add into the existing environment there and do it in a safe manner.
All right, and I'll take one last question. I'll combine, okay, so we've got one from Joseph. What are your target industries and build times by volume?
Terrific question. So we tend to play in the areas where you need composite parts. You need strong and lightweight parts. So either that or where you have particular material properties that are required for heat or chemical resistivity. So we're seeing a lot of activity in aerospace, automotive, defense, a little bit in high-end athletic equipment, but then we see funny things. For instance, we're seeing a lot of activity within solder pellets for semiconductor, or for making PCB boards. And the particular dynamics that you have of having the chemical resistivity and the heat shock of it make this a really good application for it. Our build times, we can do currently about 50 cubic centimeters an hour. So that's about an inch of Z on a 12 by 12 plate every hour and a half there. So, and we're working on improving those speeds. The machine and the technology should scale pretty well. That's independent of the complexity or the number of parts in the build. It's a fixed amount of time per page. So it's really just that rate independent of what you're printing.